Okay, good morning, everyone. So the last time we learned about SMTP, Standard Mailing Transfer Protocol. And we also learned about web caching and web cookies. So let's quickly go over them first. So SMTP actually came as a solution for inter-organizational mailing, right? Previously, mail, which was the earlier version of the mail, not the internet mail, it was used within organizations. So different hosts, different computers in an organization wanted to talk to each other, so they were sending each other mails in the format of hostname at some machine, or the username at some hostname machine. But then they wanted to do this between the organizations, across the organizations. So instead of now mailing device to device or username to username, because addressing a different username in a different organization is difficult, now they set up these mail servers in organizations. So here's my organization, the NUS organization. I have one mail server. Everyone sends their mails through this mail server. And when some other organization sends us mails, we also receive those emails in the mailing server, and then we have another protocol for pulling emails from the mail server. Because as you remember, SMTP is a push protocol, meaning that when you send a request as a client, you're sending a request to send a mail. You're not receiving, unlike HTTP. And therefore, we had other protocols such as POP, IMAP, or we can also use HTTP to pull mails from mail servers. And then we looked at web caching. We learned how it reduces the time to receive certain files or certain objects from the web servers, so it can improve the user perceived performance. And then we also looked at cookies, and this is how web servers or websites, companies can track your data. And in the case of third-party cookies, even if you do not visit that website by clicking on some ad link or something, you can still, your browser still can send a request to that third-party website through references in the ad fields in certain websites. And then we started with DNS, and this is what we are going to continue on today. So we have seen this higher-level hierarchical view of DNS. So at the top, we have the root DNS servers. These are the first point of contact if the name cannot be resolved, if nothing is stored in the cache. And then one level below, we have the top-level domain, or the TLD DNS servers. These are responsible for certain domains like .com, .org, .sg type of domain names. So after contacting with the root DNS, a root DNS will tell you the IP address of the relevant top-level domain DNS server, and then your local DNS server will contact that. And then from there, it will learn the IP address of the authoritative name server responsible for resolving that IP address. And then it will contact the authoritative name server, which is the final and the authoritative point of contact for resolving a hostname. And apart from resolving host names, we also talked about some other functions DNS is performing. They can perform host aliasing. Some websites may have multiple names. Some of them may have www in them, or it doesn't matter if you enter www or not. So this is kind of host aliasing. They can also perform the same for mail servers, and they perform load distribution in the case of CDNs, which I did not focus much on because you will learn about that in the multimedia chapter. So instead of going through the same iterated and recursive DNS query examples, let's go over that through another type of diagram, which we also saw in the case of HTTP request and response exchanges. So let's say this is my local device, your computer. It will send a request to someone. Let's say this is the timeline for your local DNS server. And then this is the TLD server. This is the root DNS server. This is the TLD server, authoritative server, and your destination. Okay? Let's also write that. So this is our client. In other words, your device. This is your local DNS. Okay. This is your root DNS. This is top-level domain DNS. This is the authoritative DNS. And this is some web server that you want to contact. And let's say this website is x.y.com. So you know this web address, but you don't know the IP address of this host. So this x.y.com can be something like maybe tech.enterprise.com. So instead of writing the same, I'll just abbreviate it as x.y.com. So the first point of contact, if your client, your browser cannot resolve the name, meaning it did not store, it did not cache that IP translation, name to IP translation, is the local DNS server. So your client will send a query to your local DNS. And what will it include in the query? I'll also write the format. It will query x.y.com, meaning I want to learn the IP of this. And here then local DNS, if it did not cache that, it will then go to the root DNS server. Hey, I want to learn x.y.com. Does the root DNS know the IP address of x.y.com? It doesn't. It doesn't store name to IP translation for the for the servers other than the TLD DNS servers. So what it will do is instead it will tell you the IP address. I'm going to indicate that as a response for x.y.com. Here is the TLD server, and its IP address. Okay, instead of writing x.y.com, let me maybe write in this format. So for .com, here is the IP address, maybe 2.2.4.0. Okay, so now your local DNS learned about the TLD DNS IP address. It can then contact this TLD DNS server. So it can send a query. I want x.y.com. And then the TLD DNS server will say, well, I don't know x.y.com's IP address, but I know the authoritative name server responsible for resolving x.y.com. So in the enterprise of y.com, so for this company, here is the authoritative name server, 1.8.4.0. These are just arbitrary numbers. So this is the authoritative DNS server's IP address. So now that my local DNS learned about that, it can contact the authoritative DNS server responsible for that. The same query, I want to resolve this. And because authoritative name server's job is to store that, it will just reply. In the response, it will tell the IP of the desired host name. Something like this. And does it end here? Well, obviously not. Our purpose is to inform this client of that IP address. So it will just forward the same response there. So this will be the same response. Any questions on this so far? Okay. Now let's assume that a few seconds passed, and then this client or some other client using the same local DNS server requested another name-to-IP translation. This time, instead of x.y.com, it requested, let's say, a.y.com. So it's maybe customer.enterprise.com, maybe customer relations division of the same company. So it uses the same authoritative name server to resolve that IP address. So then what happens? Again, because my client doesn't know, I was using red here, because my client doesn't know the IP address, it will send a query. What was the name? a.y.com. a.y.com. So now my local DNS also doesn't know the IP address of a.y.com, but it already knows, and it may have already cached the authoritative name server resolving for all y.com domains, all y.com domain names. This. So now it doesn't have to go through the same contacting root DNS and then contacting TLD and then contacting authoritative DNS servers. Now it can directly go and contact this authoritative name server for a.y.com because it already knows the IP address of this name server, of this authoritative name server. And then it responds to my client. But obviously, the purpose of the client in making these DNS queries is to contact the server, which I did not show here, but separately, after this name-to-IP translation is performed, this client is obviously sending perhaps HTTP requests to this server, which I didn't show. Okay, any questions? All right. So I said that this local DNS may have cached certain DNS information, certain name-to-IP translation, right? How long to cache such information will be indicated by the TTL field. So this is one of the fields in a DNS record. Until that TTL expires, it holds that information in its cache. But of course, the actual IP might have changed, or the original DNS record might have changed before even TTL expires. In that case, it will send a stale response, and the name cannot be resolved. Well, after all, this is just a best effort service. There is no guarantee that the DNS response will be correct. Yeah. So there are many types of DNS records. So this is how it is kept in a database. This is completely different than how DNS requests and responses are made. But there are many ways to store DNS records, but in all of them, this format is followed, this resource record format. So we have name, value, type, and time to live field. Name to value will depend on the type of DNS, and I'm just going to show a few of them. So again, this is not for memorization or anything. I'm just showing some examples here. But maybe type A is the most fundamental one, so let's learn about it. So in the type A, it is the simplest form of name to address translation. So here, name is the host name, and the value is the IP address. Very simple. So just like in the example I showed, that in this case, name would be x.y.com, and the value would be the IP address of that server or the name server responsible for resolving that IP address. In the NS type, so this is what was sent by the root DNS and the TLD DNS. So root DNS and the TLD DNS will store these NS type records. And in doing that, they will associate the name of the certain authoritative name server with certain IP addresses. For example, how does this root DNS server knew that x.y.com can be resolved by this TLD server, this .com TLD server? Because it keeps the record that for resolving, I'm writing RR here, for resolving x.y.com, you need to contact this .com related TLD server. I'm just going to call it maybe DNS1.com. This is just an arbitrary name. This is just the name of the TLD server. And because this is an NS type record, it will be NS and some time to live. So this is how a resource record will be recorded in a root DNS server. Well, similarly, for the TLD server, how does this TLD server know that for resolving x.y.com, you need to contact this y.com? Well, because it will keep a DNS record, a resource record, in the format of for resolving x.y.com, you need to contact maybe authoritative.dns5.com. So this is the name of the authoritative name server, and this is an NS type record and some time to live field. Okay, now my question to you is, if it keeps these kinds of records, how did it reply the particular IP address? Because in this record, there is no IP address. It's only names in the NS type record. Any guess? Yeah? So this was NS type record, right? Name and value. But it doesn't include the IP address. So in addition to this NS type record, these root and TLD DNS servers will also hold type A resource record, name to value. Then, in addition to this, for instance, for the TLD server, it will hold another resource record saying for auth.dns5.com, what was the IP of that? That was 1.8.4.0. This is the IP address. This is an A-type resource record and some time to live field. So this is what we store in the TLD. The TLD DNS server. And similarly for the root DNS server, there will be, another resource record of type A. Some information here. I'll not write the same thing here again. Okay, any questions? Yes. When the time to live expires, it will be deleted from the cache of the local DNS server, and the local DNS server will need to make another query starting from the top layer, from the root DNS to the TLD. Okay, I think I got your confusion. So this TLD does not relate to how long it is being stored in the root, TLD, and authoritative name servers. It relates to how long it is stored in the cache. Yeah, thanks for reminding that. That's a good point. Okay, so these are permanently stored. This is not cache. But this TLD is for indicating how long it shall be stored in a cache. So your local DNS server may delete that information after TLD expires. And there are many other types of DNS records. Well, one example I'll show is this CNAME type. Here, this is for the alias names. For instance, www.ibm.com is in fact server east.backup2.ibm.com. So it doesn't matter which one you enter in the URL field of your browser, it doesn't matter which one you send your HTTP request, it will still be resolved to the same IP address. And the CNAME records records that information. And in the MX type resource records, well, it is pretty similar to type A, but it is for mail servers. So instead of a web server name, now it is a mail server name. That's the only difference. Well, again, I'll show, just to satisfy your crave for knowledge, I'll show some formatting of the DNS protocol. But again, this is not for memorization or anything like that. So just to give an idea of how it looks like. So here we have a message header, some unique identification number, 16-bit. And this is used to identify the queries and responses. So when you quote the same query number in the response, you'll receive the same query number. So just like sending a request to a tech support team, they ask you to record your query number, right? So that in every email, every following email, you can quote the same number. It's the same thing. So here are some flags to indicate whether this is a query or reply, whether you want recursion or you're fine with iterative queries, and whether the reply is coming from an authoritative DNS server. So there are some questions here, meaning what type of query, what's the query, what IP address you want to resolve, and the answers if this is a response. I think this level of detail is more than enough. Yeah, and for the authority, it records the name of the authoritative servers and the IP addresses of them, and so on. Okay, now let's see an example again of how recording your new server into the DNS servers works. So let's say you started up a new company. It's called Network Utopia. And you want to register your company's domain name, networkutopia.com, at a certain DNS registrar. So DNS registrars are the guys who store that resource records. They can be in the TLD servers. They can be in the root DNS servers. But we are inserting our records into a TLD server because I'll explain why that is. So in a DNS registrar, we need to provide the names and the IP addresses of our authoritative name servers, right? So what's the job of the TLD? It tells you the authoritative name server name and the IP address, right? So as a new company or as a new domain, we are starting up our own authoritative name server. Maybe it's within our company, or we are buying some hosting service somewhere. But still, for TLD servers to point to our authoritative name server, we need to inform the TLD servers, right? So just like this, let's say you moved into a new place, you inform the government or whatever authority you have that you moved somewhere so people can access you from there. So it's a similar idea. When you set up a new name, you need to inform the authoritative, you need to set up an authoritative name server, and you inform a TLD server to point to your authoritative name server for resolving your IP name, for your IP address. So you insert, or you ask the TLD server to insert these two records into the TLD server. So the first one is an NS type resource record. This is your host, and this is your authoritative name server name. And because this is pointing to an authoritative name server, this is an NS type resource record. But obviously this is not enough. The question I asked you, why this is not enough? Well, because it doesn't show you the IP. Then how does a querying host knows the IP of the authoritative name server? Well, we have another A-type resource record here. And this is for resolving the authoritative name server into an IP address. So if they record these two, then our authoritative name server's IP can be resolved, and any querying client will be able to learn the IP address of our authoritative name server. But then it doesn't end here, right? They also need to query our authoritative name server for our host name's IP address. And for that, we create this authoritative server type. We create this authoritative name server and include a type A record for networkutopia.com. So how does it look like then? It will be something like networkutopia.com and our IP address, 255.0.16.4, and this is an A-type resource record. So this will be stored in our authoritative name server. And if you have also a mail server here, you can also have another MX-type record for that name server. Any questions on this? Okay. So I'll also show you how it looks like in my website. So this is the hosting and the DNS service I'm using for my website. Let's log in here. So for hosting this website, obviously I'm not hosting it at home or anything like that. I'm using some web hosting service. So some company is building mail servers and hosting people's websites. And I'm also using their authoritative name server for recording my A-type DNS records. And I also ask them to insert these NS and A-type records to point to my authoritative name server. And these two records are inserted into a TLD name server. So now you're going to see how my resource records look like in the real life. So these are my name servers. These are my authoritative name server names. Let's go into this. Yeah, you see the same names here. In fact, I can insert records here. So as you see, there are many types of records, but some of the things we learned. This A type, the name to IP translation, MX type for mail server. We have C name for canonical names, and we have NS. So just like what we learned. Well, there are other types, but I think this is more than enough. And you're indicating the name and points to, so this is the value. Where does it point to? And you have the time to leave. You can specify all these. So just like what we learned, it has 4 fields. So you can add records, but let's look at what records I already have. So ignore the other ones. So this TXT is for indexing it for Google. But here's CNAME. So this is for canonical names. So it means it doesn't matter if you enter this into your URL or if you enter it with triple W's, it will be resolved to the same IP address. And this is the record of that. Is it too small? Yeah. We have A type for file transfer protocol, I think. But anyway, ignore that. So these CAAs are for certificate authority. So in fact, although we learned HTTP, most websites in the web now run HTTPS, meaning that they run transport layer security. And in the transport layer security, we're going to learn some of that in the last chapter, so don't worry about it yet. There is some authority called certificate authority, which provides the evidence for people's identity, for web servers' identity. And in other words, it signs the public key of these web servers. But anyway, that's a discussion for later. And the CAA type resource record here is pointing to that certificate authority for anyone who wants to who wants to ensure the identity of my web server. Some MX type resource records here. This is my mail server's name. It looks like a scam name to me, but mx1.titan. But anyway, NS is, okay, so these NSs now are pointing to my authoritative name server, right? So whoever wants to learn my IP address will be, it will require this NS type record, and it will show the IP address of my authoritative, sorry, it will show the name of my authoritative name server, and then there is another record, A-type record, to show the IP address of my authoritative name server. So this NS, together with this A-type record, will be enough for anyone to learn learn the IP address of my authoritative name server. So the formatting here is a little bit different. There are some zeros here, but don't worry about that. It's just a formatting thing. And there are also TTLs indicating how long each field, each resource record will live in the local cache, local DNS cache. Any questions? Okay. Okay, so with that, we completed our study of the application layer, but we are also going to look at the socket programming. So what we learned is we learned about client-server architecture and peer-to-peer architecture. We learned about service requirements. So some applications may require reliability, bandwidth, delay. Well, using TCP can provide some of those guarantees, but you can also build these services in the application layer so that your applications can run reliably, securely, with low delay, and so on. Of course, as long as the underlying network can support that. We learned about certain popular application layer protocols, like the web's application layer protocol, HTTP, the mailing transfer protocol, simple mail transfer protocol, and because it is a push protocol, we also use POP and IMAP to pull from the mail servers. We learned about web caching, web cookies, and we also just learned about DNS. So these summarize some of the most important and commonly used application layer protocols. But some others that we didn't learn is perhaps file transfer protocol. It's used for sending typically large files between devices. And many other proprietary protocols that are not defined in the RFC documents. So these are all defined in the RFC, request for comments documents, by people who are developing these standards. But of course, for instance, for Zoom application, it may have its own proprietary protocol. If you're writing a new application, you can choose using these. Well, it allows you interoperability. You can easily link your application with other applications, other hosts, other clients. But there may also be benefits in building proprietary applications. Well, it can be your secret. You can use it as a trade secret, for instance. You can patent it to some degree. But if you're using these, again, these are all public protocols. Any questions on the application layer? Otherwise, I'm going to pass to socket programming. Okay, I'm going to pause here for a little, just for you to digest the information, and then maybe someone might ask a question. So how many of you are familiar with any programming language? Just any, can be Python, C, Java, JavaScript. Okay. So the CA2 will involve socket programming, but we're going to go over it, at least the socket programming part of the assignment, very slowly. I'll be showing it using Python. I think it is probably the easiest to use. So you can use Python, but you can also use any other programming language of your choice. Obviously, there are certain libraries that I will prohibit using, especially in Python, and I think in Java and C++, there are also certain libraries which allows you to program sockets very easily using higher level libraries, HTTP-related libraries. So you're not allowed to use those in the socket programming assignment. I'll specifically indicate that in the assignment document. The purpose here is to learn socket programming. So you'll have to do socket programming manually, meaning that you'll have to write HTTP requests and responses manually, create sockets manually, rather than using something like HTTP requests library. So yeah, don't worry if you are not familiar with any programming language. I'll go through it very slowly. And you can browse the web. You can use any resource you want. You can ask to ChatGPT. It is pretty good at programming. In fact, it did last year's assignment very well. So you're allowed to use that. You're allowed to use any resource over the internet. But please cite any resource that you use. So for instance, if you used ChatGPT in response, or at least part of the response, or at least to iterate over your response to a question in the assignment, cite that in your submission, saying, I used ChatGPT here, but then I iterated over it, I improved it, and so on. So I think it's not realistic to expect for you to not use resources like that, and I think it's not a good way to educate. Well, when the calculators were invented, imagine what happened if we prohibited using calculators. So I think it's not very different here today. So let's get started. So in the application layer, I mentioned about sockets, right? Sockets are the API, application programming interface, between the application layer and the transport layer. And in this chapter, we are going to learn about programming sockets, programming UDP sockets and TCP sockets for a web application. So a typical network application consists of two pair of programs. So one program at the client side, namely your browser, and another program at the web server. And when these programs are executed, meaning they are compiled and run, they generate processes on both ends. And the way they communicate is through sockets. So as you see here in this diagram, we have application at the client side. Oops. We have application at the client side, and we have an application at the server side. And the application process at the client side shows the message out of the door, or the socket, and it goes down all the layers, goes through the internet, all the routers and switches in the internet, and goes up again through the socket. So it relies on the socket at the other end to carry the message to the application process running on the host side. And all these in between, down from transport layer, are controlled by the operating system, or the hardware of the device. So as an application programmer, you do not have to deal with any of those. All you need is to write your application program and how it interacts with the socket. This is also the way of writing APIs. You write a program, and you also define how that program interfaces with other programs. So if you're, for instance, building, I gave this example earlier, if you're analyzing some company data and making financial predictions out of that, all you need to know is how to interact with the application programming interface of some data provider, so that you get the data from them and then run your own internal programs. So we'll be looking at both UDP and TCP sockets. As you learned in the transport layer, UDP is unreliable datagram, and TCP, it is reliable. We have flow control, we have congestion control, we have ordered delivery, and so on. And by looking at the socket programs, you'll also be able to understand why it is more connection-oriented. So this is the example we are going to use for writing our socket programs. So here, the client, this is a very simple program. So the client writes some words and sends it to the server. Server receives it, and server capitalizes all the letters in that string and sends it back to the client as capitalized. That's it. So it's a very simple program. The purpose here is not to write a complicated program. It's just to show how socket programming works. So we are using a very simple program here. So in the UDP, let's start with UDP. We are going to be looking at both the server and the client programs. There is no connection between the client and the server. There is no handshaking. And the sender needs to attach, because there is no connection, sender needs to explicitly attach the destination address and the port number to each packet. And then receiver extracts the sender IP address and the port number from the received packet, and in sending its own response, it will use these IP address and port numbers. And because there is no connection, each transmission is treated independently, right? The transmitted data may be lost, or it may not be received ever. Or it may be received out of order. And from the application point of view, we can say that UDP provides unreliable transfer of bytes. In other words, groups of bytes is datagrams between the client and server processes. Okay, so let's go over that very, very slowly. So here's my server, and here's my client, right? Well, the client, the server obviously should have created a port, and it should already be running an application, right? Because the servers are always on. So it created this server socket. Let me use another color here. I think blue will do. So this AF INET is to indicate this is IPv4 socket, so IP protocol version 4. Now there's also IP version 6, so for that there would be a different parameter here. And this SOC diagram indicates that this is a UDP datagram socket. So for TCP, we would have a different thing here. So what it does is, so what this thing means is that it is instantiating a socket object with the name server socket with these attributes, AF INET and SOC diagram. Well, the client does something similar. It creates a socket. Same, it is Internet version 4, and it is a datagram, a UDP datagram socket. So it creates this datagram with the server IP address and port number X, and sends the datagram via client socket. So here we are not specifying the client's port number and the IP address when creating the socket. Why is that? Again, the operating system provides it for us. Right? But how do we know the port number and the IP address of the server? Again, I repeat, we do not have to provide the client's IP address and the port number to our client program, because the operating system attaches it for us. It is done in the transport layer. But we need to attach the server's IP address and the server's port number. So how do we know that? I'm sure all of you know this. Come on, I think you all know this. How do we know server's IP address and the port number? Well, you know your server's host name, right? When sending a request to any website, you have to know the URL. You have to know the host name, and that host name is resolved through a DNS server. So your client program will incur a query to your DNS to learn about the IP address corresponding to a particular host name. That's how you know the host name or the IP address. And for the port name, again, we know the commonly used port names for certain protocols. We know that HTTP uses port number 80. SMTP uses port number 25. So you also know the port name. You already know these, so this is how you include them. Anyway, so we created the client socket, and the server created its own socket. And then our client will send the datagram, and the server will read the datagram from the server socket. It will run its own algorithm. In our case, it is just capitalizing the letters of the sent message. And it will write the reply again into server socket. And it learned about the client's port number and the IP address when receiving this datagram here. So it will send it to the same IP and port, and the client will read the datagram from the client socket, and they will both, the client will close the client socket. The server may keep it open if it wants. Okay, so it's a very simple program. You create your socket. The server has created its own before. You send the datagram. Server does whatever it wants to do, and it sends you back. There is no connection. There is no reliability. There is no guarantee that you will receive it or it will be lost somewhere. It's just the best effort service, just one-off thing. Very simple. Now we're going to be looking at the actual program doing that. So this is the UDP client program. So the client begins by including this Python socket module by writing this from socket import. So this, by using this line, we'll be able to use Python's all the socket-related methods. And this is also how I want you to do it in the assignment. If you're using Python, if you're using other languages, there are similar libraries in pretty much any popular language. And we are indicating the server name and the server port. Again, if in the place of in the server name field, if you are writing an IP address, that's fine. If you're writing a host name, a website name, www.nus.edu, a type of name, then it will incur a query to DNS servers, and it will be resolved to an IP. And then we are creating a client socket here. I just said this is for IP version 4, and this is for indicating this is a UDP datagram. Again, we are not specifying the client's port number when creating the socket because the operating system provides it for us. Then we are assigning whatever the user writes in the keyboard into this message string. So this row underscore input is a function in Python. After you write this, whatever you have in the parentheses will be printed, and then whatever the user writes into the terminal or the console will be assigned to that string message. And then, so it gets user keyboard input. And then with this send to method, we will send the first field, the message.encode, to this server name and the server port number. So it's just a method. So what we did here is that we created a socket object with the name client socket. In the object-oriented language terms, this is creating an instance of a socket object. And using the send to method, notice how we are including the to. It will be different from TCP. It indicates the server's name and the port number. Because it is a one-off thing, you have to indicate where this datagram is going. Whereas in the TCP's case, we'll learn later. Once we have a connection, we do not have to include the server name and the port number every time because we already have a pipeline towards that host. And then, well, we'll just keep listening on our port in case server sends us a reply. And with this receive from method, client socket.receive from, and this 2048 is just some buffer size. We are listening the client socket, and whatever we receive, we assign it into a modified message, and we are also assigning the address we receive it from into server address. Well, we do not use a server address. We already know the server address, but this is how receive from is structured. Now, we receive the modified message, so we are just printing the modified message, and then we are closing the connection. Okay, any questions on this? Okay, yeah, this is really simple. Now we look at the server side for the same communication setting. Similarly, the server imports the socket module by using the first line, and it creates a socket with the port number here. It creates an IPv4 socket, and it indicates this is a UDP datagram socket. And by using this bind method, it binds that socket to a particular port number. In this case, it is assigning port number 12,000 to this port. And why do we have to use port numbers and we have to assign different port numbers to different processes? Well, because the server may be running multiple processes simultaneously. And this is a huge computer maybe running multiple processes, and every client might want to access a different process on the server. And by indicating their port numbers, the clients will be able to connect to their desired processes. That's why we have port numbers. So if this same port number, 12,000, was already in use by another process, the bind method would fail here, and it should have given an error. While this program is a very simple program, it doesn't check for exceptions. So if it fails, the program just fails here. So in writing your program again, make sure that you're not using the same port number for two different sockets. And then we are printing some line, server is ready to receive, and then we have an infinite loop here. Infinite loop for listening to that socket. So whatever the server receives from this socket, from the server socket, with some buffer size, it will assign it to the message, and it will also record the client address. Well, it will run its own algorithm. In this case, this is just converting it into uppercase letters, capital letters, using the upper method, and store the modified message in here. And then it will send, using the send to method, the modified message to this client address. And what's the point of looping here? Well, your client, because the server is always on, right? It keeps waiting for client queries. So after a while, client again sends another request to this server, another message to this server. This server will be able to reply because it keeps, while true, this is always true, so it keeps repeating this indefinitely. Okay, any questions on UDP programming, UDP client and server programming before we pass to TCP? Okay. So in TCP, the client needs to connect to the server first. So in UDP, we only had one socket, right? In TCP, we have two sockets. One is the welcoming socket, and one is the connection socket. So let's think about this analogy first. When you take away food from a restaurant or when you go to a hawker center, you just order your food, get your food, and then go to home or eat it. That's just one-off thing. You order and you receive. That's like UDP. But when you go to a full-fledged restaurant, I'm not talking about McDonald's or self-service restaurants here, but let's say some high-end restaurant. Not necessarily high-end here. You're usually greeted at the entrance, at the door. So some waiter or waitress will greet you there. That will be the welcoming person. And they will accompany you into a seat, into a table. And from that table, you'll be served by another person, another waiter or waitress. So that person will run another process. That person will take your orders. And while you're seated there, you can order repeatedly. You do not have to go back to the welcoming person again and enter the restaurant again, but you can just keep ordering in that table. So this is like TCP. In TCP, we have one welcoming socket. That socket welcomes you and establishes a connection. And it assigns another socket to you, the connection socket. And through that socket, you're already connected to that socket. You can send as many messages as you want. So here the client contacts the server by creating a TCP socket, specifying the IP address and the port number of the server process. This is for the first welcoming socket. And after this is done, TCP connection will be established. And then the server will be assigning a new socket, this connection socket, to the client to communicate with the client. Same as the UDP, we can assign different connection socket port numbers for different processes and for distinguishing between different clients. And by doing that, we can provide reliable and in-order byte stream transfer. You can think of this as a pipe between the client and the server. And therefore, you do not have to specify the host's port name and the IP address in every single message you're sending. So now let's see the diagram of TCP client-server interaction. So again, we have our server, we have our client, and the server is creating a socket at some port number for incoming requests. And remember that unlike UDP, TCP is connection-oriented. That means before the client and server can send messages to each other, they need to handshake, the three-way handshake of the TCP, and establish a TCP connection. So as the server is waiting for incoming connection requests at the connection socket, the client also creates a socket and indicates the host address or the host ID and the port number. And once this connection socket is established, we say that TCP connection setup is done. So during this three-way handshake, it's like the client process knocking on the welcoming door of the server process. And when the server hears the knocking, it creates a new door, what we call the connection socket. After this TCP connection is established, the client will send the requests using this client socket or the connection socket at the server side. And the server will receive it at the connection socket and reply from the connection socket into the client socket. And then they can both either close their sockets or they can just repeat the send and receive sequences into the same connection. So the major difference here is that we have two sockets rather than just one socket. Now let's see that over an example application. Again, we are creating the same application that capitalizes the letters of whatever the client sends. So this is our TCP client program. Again, we are importing the socket module of Python, and we are indicating the server name and the port number of the server. So this port number is the port number of the welcoming socket. The client socket now instantiates a socket object with the name client socket. Now, we are still using IPv4 AF-INET, but this indicates this is a TCP socket, sock stream. Instead of sock dgram or datagram in the case of UDP, now we have sock stream. Then, a different method, the client socket now uses this connect method to connect to the server name at that 12,000 server port number. And in the same way we are writing the sentence, we are expecting the user to type the sentence in lowercase letters. And we are sending that sentence into the client socket using the send method. So remember in the UDP's case, we had send-to method. And in addition to the message, we also indicated the IP address and the port number of the server. So the reason we do not use send-to method, but we use send method here is that we already connected to this connection socket of the server. So it's like we already have a pipeline going directly to the server. So we do not have to indicate the IP and the port number of the server again and again. Oops, okay. And then after sending it, we keep listening for some buffer size. And whatever we receive, we assign it into a modified sentence, and then we print that modified sentence, and then we close the socket. Any questions? Okay, so I have a question for you to think about. And ideally, I expect you to respond, but we're a bit silent today. So I said that in TCP, and you learned in TCP that there is three-way handshake. Where is the three-way handshake in this program? Connect? Well, you're right in saying that during the connect, the three-way handshake happens. But it is done in the transport layer. So your application layer program doesn't specifically include these three lines. In fact, you're sending two packets, right? The SYN and SYN-ACK, and you're receiving ACK also. So in other words, the client is sending SYN, receiving SYN-ACK, and then sending ACK, correct? But that means we are sending two packets. But we are not sending two packets here. So you're right in saying that during that connect phase, it happens. But we do not have it here because it is done in the transport layer. Again, in writing your program, you only deal with the application layer and how it interfaces with the transport layer. You do not have to deal with how you use TCP, how you send 3P handshake messages, and so on. So it is what happens in the transport layer is completely invisible to the client and server programs. Now let's look at the TCP server. Again, we are importing the same socket module, and we are indicating the server port number here to about 12,000. Again, this is the port number for the welcoming socket. Now, I indicated these two connection socket objects by two different colors. So the first one, the green one, the server socket, is also called welcoming socket. And the orange colored one is the connection socket. Now the server socket is created, an object, a socket object is instantiated here. Again, we are using IPv4 and indicating this is TCP socket. With the bind method, we are binding the port number into that socket, and we keep listening for one packet. We are printing this line. The server is ready to receive. And again, we are looping, just like in the UDP's case. We are entering an indefinite loop, because the server socket will keep listening for any incoming requests, any incoming TCP connection requests. And whenever it receives a connection request, it will assign a connection socket to it. So just like in the restaurant example, some guy is at the entrance of the restaurant. He'll be waiting like this. And so you enter my restaurant, I accompany you and bring you to my table, and then I will ask another waitress to serve you. And then I'll come back here at the entrance of the restaurant, and then you will come, and then I'll accompany you to another table. So I'll have to keep listening. I'll have to keep standing at the entrance of the restaurant. So it's the same thing here. Our server socket, or the welcoming socket, keeps listening, and whenever it receives a connection request, it accepts and creates a connection socket with the address and assigns the address of the person or the client that is requesting to connect into this address variable. And we will then receive our orders or our sentence from our connection socket using the receive method. And we will then run our own algorithm here. In this case, we are just converting it into uppercase. And then, again, through that connection socket, we will send the capitalized sentence. And, well, in this example, the server program immediately closes the connection socket. But you do not have to close the connection socket. You can keep it open for a while in case the clients order something. So this program would be something like a restaurant, which only allows you to order once when you're in the table, and then you have to go out and then come in again. But the connection socket can be kept open for you to receive more packets through that same connection socket. But again, this is a very simple example. Any questions on this? Give me a moment. And when I said we close the connection socket, we're only closing the connection socket. We're not closing the welcoming socket. So that guy is still at the entrance, all right? Yeah, yes, please. So it can work with multiple clients, but this program, as it is designed, it doesn't work with multiple clients because we are assigning the same connection socket name for only one client here. If you have multiple clients, you cannot assign them both to the same connection socket. But in your assignment, you might need to create multiple connection sockets if you are dealing with multiple clients. But yeah, as the code stands here, it doesn't support. Yeah, any questions on TCP server and client? All right. So we already did some recap at the end of the application layer, but yeah, again, we looked at application architectures, we looked at service requirements, we looked at Internet Transport Service models, TCP and UDP, and we also learned how to program sockets using TCP and UDP. And most importantly, we learned about some of the popular application layer protocols. We saw how both HTTP and SMTP are typical request and reply message exchange. The client requests for some service, and then the server provides that service in return. We looked at message formats. HTTP message formats and SMTP both are very easily readable in ASCII format. We looked at DNS format, how resource records are structured, and how DNS messages are structured. We learned about some of the important themes, centralized and decentralized, stateless. We said HTTP is stateless, but to keep states, we can use cookies. But the programs that are keeping states are difficult to implement because what happens when a client disconnects or fails, they need to reestablish their state. They need to update each other on the state. We looked at some of the scalability issues. For instance, in the case of DNS, we want a hierarchical structure, and we want to keep the complexity at the edge of the network rather than implementing some essential service like DNS in the core network. We want to pull all the complexity to the edge of the internet and run whatever we can at the application layer. So this is the internet's main principle. And that concludes our application layer study. So as I said, I'll be releasing the socket programming assignment soon, perhaps over the weekend. So I'll give you about 4 weeks to complete it. And I'll also be releasing the next tutorial. I believe it's tutorial. I already did. I released the tutorial 4. That's on application layer. There are, I think, 3 questions there. Only the last question is about mobility, so you can ignore that, but solve the rest. You can attempt the rest, and I'll solve the questions sometime next week in class. Okay, any questions? Yes. Yeah, come again? Yeah. Thanks for reminding that. So on Friday, we'll be covering wireless networks and mobility. So again, I'll upload new slides for that, probably today or tomorrow. I think it will take us about a week or 2 lectures to cover that. After which you can attempt the last question of the current tutorial I uploaded. Any other questions? Okay then, see you on Friday.